All right, earthquake analysis. Let's talk about how we can analyze this seismogram to figure out all this information that is here. So I'm going to start with the P arrival times, which are kind of indicated by where this P is located on this time scale here. Now, just a heads up, these numbers 101 represent 1 hour and 1 minute, and all the places in between would be seconds. So if you look, this is 1 hour and 1 minute, and this is 1 hour and 2 minutes. So these lines go by seconds. In fact, they're 20 seconds. So this would be 101 and 20 seconds. This would be 101 and 40 seconds. And then this would be 101 and 60 seconds, which is just 102. Okay, so if we want to analyze exactly where this P wave comes into this time scale, I'm just going to come straight down from there. And I'm going to estimate that that's right before this line for 108. So I'm going to say that the time is 1:07. And then we just have to guess how many seconds that is. And to me, that's probably somewhere close to around 55 seconds or so. Okay? Now, S wave, if I come straight down from here, again, that might be right on the line, maybe right before the line. But you can see that's 109, and this is 20 seconds over. So we know that the time is definitely 109, and it's going to be somewhere approximately, we could say 20 seconds. In fact, let's just call it 20 seconds because it's pretty close to the line anyway. And that little bit of difference is not going to make a humongous difference. Lag time. Lag time is S minus P. So we're going to subtract these two numbers here. And I'm going to do that over here just because this is one that you really want to set up mathematically and subtract. And there's a definite trick to this one. 107.55 is my P arrival. 109.20 is on top. I'm subtracting. And if you notice, I can't really do 20 minus 55. That would give me a negative answer. So what I'm going to have to do here is I'm going to have to borrow from the minutes column. So I'm borrowing a whole entire minute. This becomes 8 minutes now. And now, because I borrowed a minute, I'm adding 60 seconds to this column. So this now becomes 60 plus 20, which is 80. 80 minus 55 is something that you can now do, right? And you know that that is 25. Now, 8 minus 7 is 1, and 1 minus 1 is 0. So that's 0 hours, 1 minute, and 25 seconds. So I'm going to write that over here. 0 hours, 1 minute, 25 seconds. Now, epicenter distance. Epicenter distance is something that you will have to use your reference table for. So I'll pull my reference table over and just zoom out a little bit here. Okay, and now what you want to do here is what's called the wedge method. Now, the wedge method requires using an extra piece of paper. So I'm going to take this extra scrap piece of paper. I'm going to put that right on the side of my y-axis. I'm going to mark where 0 is. And now I want to mark where 1 minute and, our lag time was 1:25. So I want to mark 1:25. That's about 1.5 or close to. So right around there. Okay, it's just above that line for the 20-second mark on here. And now what I'm going to do is I'm going to take these two marks, I'm going to slide this up until it fits in between them. And I don't have to go very far, keeping this paper vertical. This is the wedge method. And again, it's going to wedge somewhere around in this neighborhood, not very far up. So here's my P wave, here's my S wave, and it fits in between right around here. So if I go straight down from there to my x-axis, that ends up being right before 1,000 kilometers, approximately 800 kilometers is my distance. So I'm going to write that down for my distance here, 800 kilometers. Now, P travel time. P travel time, again, comes from your reference table. You're going to want to look at that same distance that we had here, 800, this line right before 1,000. We're going to go up until we hit our P wave right there. And then we're going to go over to our y-axis, and it's going to end up somewhere around here. Now, to me, that looks like it's above this line, which is 140. So I'm going to say it's 1 minute and 50 seconds, approximately. Okay, so I'm going to write that down here. Now, P travel time is 0 hours, 1 minute, and 50 seconds. S travel time. S travel time, you can go up a little bit further. So we're going up 800 until we get to the line up here. And that ends up right around here. And if I go across from here, that's about 3 minutes and close to 20 seconds or so. And so I'm going to write that down. 0 hours, 3 minutes, and approximately 20 seconds. It might be more like 15. In fact, if you do 15, that'll work out with the math over here. Okay, now, origin time. Origin time is an equation, and the equation for origin time, I'm going to write this down, is equal to P arrival minus P travel. You can also do S arrival minus S travel. Either way, it'll work out to be the same answer. Okay, so P arrival minus P travel. I'm going to write these numbers down. My P arrival, which is right here, 107.55. 107.55 minus my P travel, which was 150, right here. 0 hours, 1 minute, and 50 seconds. This is nice, simple math. I don't have to do any borrowing in this example. So 55 minus 50 is 5 seconds. 7 minus 1 is 6 minutes. And this is 1 hour. So that's my origin time, 1:06 and 5 seconds. Okay? So again, from just this bit of squiggly lines on this piece of paper, we were able to determine how far away the earthquake happened and what time the earthquake happened. And if we had 2 more of these, we could actually determine exactly where that is on a map. So that's called triangulation. So there you go. Hopefully this seismogram analysis will help you with future questions on this topic.